In this video, we are going to talk about high-speed interfaces, and we will talk a lot, for example, about PCI Express, but everything is going to be applied on serial links, and it's going to be from, like, you can see generation 2, 4 gigabit per second up to I don't know how many. But Donald is going to tell us more. So what we are going to talk about?
Well, we're going to talk about what makes serial links work and what makes them fail. That's the extremely interesting topic, and the links we talk about and the techniques we talk about are going to apply to every kind of serial link out there. I mean, I say 7 to 70 gigabits per second.
Okay, so what everything else we can call this like serial link, like PCI Express is good example, correct?
Correct.
What
Yeah.
else are
Yeah.
some kind of standard interfaces?
Well, you have the disk drive interfaces like SATA and SAS. You have the Ethernet interfaces, 802 dot whatever. So whether it's HDMI, FireWire, whatever it is, at the electrical or we might say the physical level, uh, um, it's all pretty much the same. I mean, for example, you can get your basic FPGA, and that FPGA transceiver that will talk to anything and everything, right? Any one of these types of interfaces, they might throw it in a slightly different mode, but at the electrical level and in the electrons and in the PCB traces, the same things are happening.
Okay, so now let's be a little bit more specific. So what we are going to learn today, we are going to learn how to route these interfaces or how they work, or what is in your slides?
Well, okay, so what I would like to do is come in the back door, because I have tens of thousands of these links in productions across dozens of standards. I wanted to come in the back door and talk about where the issues are and explain, what makes these fail in practice. And so when we talk about the reasons why they fail, then that naturally leads us into talking about why they work. So that's my proposal. If that's how your audience wants to go, then let's do it that way.
So okay, let's start where they fail. I'm curious. So what is the most common fail?
Okay. So can I bounce over to
Yeah,
that
definitely. You
slide?
can
Yeah.
just find.
Okay. So everybody, I think everyone understands that at these frequencies, you have some loss. You don't just have a physical wire. You have something happens from transmitter to receiver that attenuates or decreases the voltage that's propagating, right? And so we call that loss. But that's not where the failures are. I mean, is that
So
surprising to you, or?
so I would like to know what are the where are the problems?
Yeah, so I mean, how could that possibly be? And loss, and so I show an example. I mean, loss is sort of an understandable problem, and it's sort of a linear problem, and it's what today's equalization in the chips is handling. So
Okay, so
we've had it.
before we continue, I'm sorry for interrupting. So we used equalization word. We would like to explain this. And I would like to
Yes.
talk a little bit about loss, because I've done some videos about loss.
Uh-huh.
And I would like to maybe mention that in these very high-speed interfaces, the loss is going to be kind of significant, and what is starting from the transceiver and what is finishing at the receiver is the signal can be much smaller, correct? That's why we need something extra to be able to
Yes.
actually read this signal, and this what is extra
Yes.
is the equalization.
Yes. Yes,
And
I
and,
think
and I would like to point. I would like to really highlight like there is really big difference between signal coming out of the transceiver to the signal which is received.
yes. And I'm going to show a picture of that, but you actually just explained it really well. So good job, Robert. In a Gen 5 PCI Express 36dB, I mean, you've got like 1 to 2% of the voltage that started at the transmitter showing up at the receiver. So this is, I'm going to show you a waveform in a second. It's just unbelievable that this unintelligible waveform that shows up at the receiver is actually recovered. Okay, that the receiver equalization, as you said, is smart enough to recover a signal. All right. Um,
So when you say 1-2%, if we have, for example, 1 volt on the transceiver, it means it's
yes.
going to be what? 1%. That's like 0.01 or
Yeah,
0.02
yeah.
volt.
10 millivolts.
Yeah,
you know
yeah,
it's
10
it's
millivolts.
barely there, and so, well, let me jump to that, being that we're talking about this. Like, believe so this is a waveform captured at the input to the receiver. Okay, so what
Okay.
you might see by the time you get to the end of this whole connection, right?
This
And
this
believe it
really
or
doesn't
not,
look like proper
no,
signal.
no, it's no, it's it, there's I mean digital's kind of it's been gone for, 30 years on the PCB, right? It's just, we think it's all ones and zeros, and these are ones and zeros. So I put them here so people would understand. Like, there's a double zero right there. So so what I think it's important to communicate is the very slightest nuance, the slightest change in even slope. If you read my PCIe Gen 5 paper, there's even more extreme examples. Just the slightest wiggle of the waveform or the change in slope indicates that you have a different logic level.
Hmm.
Okay, so so this is over here. If I wrap this waveform into an eye diagram, there is no signal. There is
Hmm.
no eye. There is no open eye, right? Okay. So so why does that work? Okay, that's the question we're asking here. Well, the answer, as you already said, is equalization. So there's there's tens of thousands of transistors in the IC, basically turning this blue signal into this red signal. So in simulators, we're able to look at what is presented on this side of the RX and what comes out on the other side of the equalization. Does that make sense?
Can you simulate equalization in simulator?
Absolutely, absolutely. In 2007, we worked out this thing called we added to the IBIS standard something called algorithmic modeling, and it's goes by the term AMI. So if you take an IBIS AMI model, then you also not only get all the analog behaviors of the transmitter and receiver, but you also get all the equalization in there.
So
Yeah, go ahead.
so this is very interesting because right now for these lower frequencies everyone is like simulating on the input of the chip or IC, and suddenly uh, this kind of measurement or simulation on the input of IC, it's kind of useless.
Well, I mean, and think of the big BGAs, right? You can't go measure there anyways, right? You can't get a probe into these things. So for the kind of the technology we've been dealing with for 20, 30 years, it's this is why we do a lot of the design virtually, right? More and more design tools and so on. So it's really only the simulator that's letting me see this. And the good news is these techniques are almost 20 years mature now, right? So they work quite well.
Okay, I have a couple of questions. So
Please.
first, is this equalization always the same, or there are different algorithms, or how do you include specific algorithm in the simulation?
Yeah. Okay. So um, that's a great question, by the way. So over the last couple decades, a lot of the techniques have, we might say, standardized in the sense of, just about, I mean, every transmitter is going to have what's called an FFE, feed forward equalizer. Receiver is going to have a DFE. I have a slide about this coming up. Decision feedback equalizer. So these techniques are fairly common, but how they are done in each chip or each IC is a function of their unique design
Mm-hmm.
and which is captured in their unique model.
Mm-hmm.
Okay. So if I answered the question there, um, there's similarities, but there's difference in design, right? Because the IC vendors are all using different, well,
Mm-hmm.
they're trying to compete with each other,
Mm-hmm.
right? So it's like, well, my equalizer is better than your equalizer. But there's similar techniques and, you know, and that's what this is showing. I mean, it's amazing. You can see the digital pattern here, right? And then when you wrap that into an eye, this is against a PCI Express mask, that little thing in black there. Like it's working. It works.
I can't believe this. Okay, so the second question would be like, is this equalization integrated in every this high-speed interface, or because even like PCI Express, early PCI Express, I think some of them they had some kind of early equalization, or there are some levels. You already mentioned this of these equalizations. So I think on the slide where we were starting, maybe you had there some information on this in the table.
Yeah, yeah. You want me to go back
Yeah,
there?
yeah, yeah,
Okay. Uh, so in this row right
yeah.
here, right? This shows from a PCI Express level what what they're assuming. Okay, now what's in real parts is much better than this, but the spec assumes you're going to have at least one what we call a tap in your TX, but nothing in your RX. Now look at what happens though, Robert. So this is transmitter slash receiver,
Mm-hmm.
transmitter slash receiver, transmitter slash receiver. Okay. So the receiver is getting more and more of the action. In fact, when I put the 64 gigabit per second column in here, it's going to go to 3/16.
Mm-hmm.
Okay. So that's amazing, that each iteration or each notch in data rate, each increase in frequency brings a new assumption in terms of how much equalization is there's going to be there.
Mm-hmm.
Does that answer the question?
Yeah. So basically, it means if someone is working, for example, with PCI Express Generation 2, then they should be a little bit more careful about doing PCB layout because it's not going to be as very well processed,
Uh,
or
I
it's
mean,
low enough so they can make mistakes.
that again, like where we started, I wouldn't say any data rate's harder than any other one. They just all have different assumptions, right?
Mm-hmm.
And if you're running at Gen 3 or something, there's a good chance your chip can really do Gen 4.
Mm-hmm.
Um, so it probably has lots of advanced capabilities beyond Gen 3. Okay, because when the link starts coming up, it'll start at 1, and then that's working. It'll go to 2, 3, 4. It'll just keep going until it's not
Mm-hmm.
working anymore. That's just what they call training or bring up or optimization.
So basically, what you are saying, if someone designs this kind of interface, it still may appear to work properly, but not at full speed. For example, even if
Oh,
it's
yeah. No, I'm glad you said that. Sorry, I kind of interrupted, but This is a huge difference of serial links because they assume going in a certain what's called a bit error rate. So in other words, the whole thing is designed and architect, we might say around failure. Like we know we're going to have so many failures, so that doesn't. In the old days of the PC, we got this thing called a blue screen. Something went wrong somewhere, and you get this blue screen, everything dies, right? Um, but the serial link doesn't do that. It will ratchet down, and it has built in these PCS layers, or not quite the protocol layer where they can recover from an
Mm-hmm.
error, right? So they every spec, and that isn't the line on the, in this chart, but every spec says, here's how many errors we're going to plan on, and call that good.
This is interesting because you know I because some people may think, oh, I routed PCI Express Generation 5, everything is working perfectly, but it doesn't mean it's really working on the top speed. And
Yes, yes.
like,
I think that's the takeaway. A serial link will look like it's working, like there's a connection, there's communication. Okay, but is it optimal? Is it working as well as it can be working? So this is part of what I mean. This is the world of signal integrity, really. Let's get margin. Let's make it work as well as it possibly can work. But that was a great question.
okay, so now I've seen you have some tips. Let's move to layout or something like this, and then we will go back to theory because I know many
Yeah,
people
yeah,
they
yeah.
do layout here. So let's be a little bit more specific, like what are the most common mistakes, or what we can do to improve layout for these
Yes,
very high speed
yes.
traces.
Yes. Okay. So
We can go
these are
back
the
to
three.
this a little bit later.
Yeah. No. This is to make my point, though,
Oh,
that
okay.
these are the most common causes of failure.
Oh, okay. I see. Discontinuities,
These
crosstalk.
three
Yeah. Okay.
things, right? So in other words, the very thing that makes it work, equalization, is also the thing that's most prone to making it fail. Okay, because that's what makes it work. So it has to be working right. Okay, but you said PCB. So these two things talk about the PCB. Okay, so what I'm going to call discontinuities over and over and over again, uh, these are places where the impedance is not matching in your PCB or your connectors, right? And so those mismatches cause a reflection. So think about this, Robert. We already said we're working in a world of 10 millivolts. So how much, reflection or signal noise is going to cause 10 millivolts? It doesn't take much, right?
Yeah, and,
So
and you
so if
mentioned the equalization is based on these edges. So if the proper signal mixed with the reflections, then it's going to be rubbish.
Yeah, yeah, absolutely. So the slightest little imperfection, I mean, I don't want to make it sound worse than it is, but again, an impedance mismatch can cause this one right here to not make it or look like a zero, right? Crosstalk as well. Crosstalk, we talk a lot about crosstalk. The issue isn't really what you're thinking in your mind right now. So I'm looking forward to explaining that.
Okay.
So, so I mean, I would be normally talking about the biggest problem first, which is equalization, but you wanted to go PCB. So
Yeah,
I'm
yeah.
going to go there. And then, and then maybe if you want, we'll come back and talk about equalization because
Okay.
that's
Okay.
that's it's you know it's a big deal. It's not something that today's
We will go
hardware
back because
engineer.
I'm curious how it actually works.
Yeah, yeah, yeah. Well, and I can't get to the bottom of that per se, but I could kind of tell you, some good places to get started with it.
Okay.
So I'm going to jump into the PCB side. Is that okay?
Yeah, yeah. I'm curious.
Just keep in mind this is number two. Okay. So uh, So I like this picture. If we had animated, you would have seen like just perfect silver transmission line, right? But discontinuities, they kind of take that nice smooth transmission line and it was 100 ohms, now it's 120, now it's 75. You see, so that's what I'm graphically trying to show right here. There's things we do or don't do in our PCBs and our connections that make this nice, what should have been a nice clean connection, and we make it kind of messy, right? Um, so I already said the impedance changes are what cause these reflections that mess up the signal, right? And so discontinuity is simply the term for what happens when that's how we isolate and how we talk about what's at the impedance change. Does that make
And
sense?
yeah, and I see in the second line you describes where this happens. So breakouts, AC capacitors, connector, vias, everything.
Well, and sadly, I can even show you just routes on a PCB where, you think it would be a nice constant impedance and it isn't. Okay.
Because of
Uh,
the mm, way how PCB is, how the material is created, because of the fiber, what is it, inside of the
five,
PCB. And
yeah, it might be the weave of the dielectric. It might be the etching process. It just might be sort of a poor manufacturing process.
yeah, I've done some
Right.
videos on this topic, so if someone would like to know a little bit more about
Ah,
where the losses are, uh, and imperfection in PCBs, then they can watch the other video.
good. Yeah, I hope you'll link that so people have what they need there. Um, so this is discontinuities. Now it seems I never stop talking about this uh, because when people call me with their failing link, this is if it is an equalization, it's going to be a discontinuity.
Mm-hmm.
Okay, there was something in their connection that they just overlooked or didn't realize it was going to present a signaling problem. Okay, so so this isn't showing you what to do yet, but this is showing you where there's information at least.
Okay.
I don't know. Is like I think it's kind of funny. I can ignore it. I can remove it, match it. I mean, do any of those jump out at you? Is there anyone you want to
Okay.
dampen
So
it?
steps. I know you have a slide on steps, so I would like to talk about steps.
Yes. Okay. Good.
And what else? Proper
Good.
ground return vias.
We'll talk about
Okay.
stubs, but
Yeah, go on the
it's
next slide. Go on the next
it's
slide.
it's a big topic. And so I've put all this online just because, again, this is where the issues are. Um, so so here's a fun little chart because, and this was captured in that where we began, right, for the different data rates. Um, it's important to realize that the size of the feature, the size of the whatever it is in your PCB may or may not be a discontinuity. Okay, so at lower data rates, I don't really like 120 mils. That's maybe an edge finger pad. Like I don't really have to worry about that at 5 gigabits per second. Okay, because that's not the signal's not going to see that. It's not big enough, right? But whoa, over here, you know, when I'm at Gen 5 going at 32 gigabits per second, all of a sudden I care about structures that are only 20 mils. That's a pad,
Yeah.
right? I mean, that's a pad under your BGA, right? So everything starts to matter is a statement I'm hearing more and more. But this is an interesting little point right here that and I give all the math in those articles and so on. Basically, we're just getting something that's the tenth of the period or the unit interval. But now your average PCB is going to be 62 mils thick, right?
Yeah.
And so at 10 gigabits per second, all of a sudden the via pops up. It's a
Mm-hmm.
discontinuity. All of a sudden I see it. Is that making sense?
Yeah, this is very
Uh,
good to point out because I know some people may worry about when to start thinking about back drilling. Uh,
right.
so this can give them an idea at what gigabits per second they should start worrying about it. And also, I would like to, I always try to point out what kind of frequencies we are talking about because sometimes people think in frequencies. They don't really think about baud
Yes.
rates.
Yes. Okay. So let's translate that real fast. It's very easy equation. All right. So for gigabits per second, the frequency, the max fundamental frequency we're talking about is always half. Okay? Because I've got one bit high and I've got one bit low, and that makes up my period. So the frequency of interest is half the number that's shown on the x-axis there.
So for
Make sense?
10 gigabits per second, we are talking about 5 gigahertz.
Exactly. Exactly. Okay. So this, but see, this is the thing that helps you, this chart helps you work a little bit smarter because, oh, I heard this YouTube that said I have to worry about the pads under my BGA, right? Well, no, you don't until you get to a certain frequency. Make sense?
Yeah,
Okay. So
definitely.
so you don't want to spend a lot of time on things that don't matter. So the first thing you need to get is your data rate, and that's why that chart we began with has the data rate across the top because things change as you go faster and faster, for basic, reasons of electronics, right?
Yeah, and I think in the table you had like PCI Express generation 3 was what? I don't remember. 2 was 5?
Well, I'm cheating a little bit. Gen 2 is really 5, but I wanted to make this thing work in terms of data rate doubling. But Gen 3 is 8, right?
Mm-hmm.
So it's at Gen 3 we start thinking about VIA. See, here's the relevant feature size shrinking,
Mm-hmm.
shrinking, 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 right? So we used to talk a lot about trace impedance. We still do, right? But then vias became important, then connector pads, and now, like I said,
Mm-hmm.
everything needs to have its impedance matched, or it becomes a discontinuity.
Mm-hmm.
Make sense?
That's why we, for example, make sometimes opening under the paths for these very high speed interfaces.
Right, right. Which is the leading cause of crosstalk, which we'll get to in a second. Those
Okay.
those openings under the pad. So you can fix one problem and create another one, right? So
So what is the problem with crosstalk?
oh, see, you can't wait. You can't wait. So, but we're going to do stubs next because you
Okay.
asked about that. But
Okay.
being that we're here and you talked about, well, do I back drill? Okay. So depending on the thickness of your PCB, you're probably not going to back drill at Gen 2. You might do sequential lamination at Gen 3, or you might start back drilling, right? At Gen 4, we were back drilling. We would maybe do 2 layers at a time. We wouldn't target every single layer with our back drill, right? But now at Gen 5, every layer is targeted.
Mm-hmm.
Okay.
So what does it mean,
Um,
like sequential lamination and two layer? Can we talk a little bit more about this?
yeah, I mean, that was an idea. I thought maybe it would catch on more than it did. I don't see too much of it in practice, but basically you have a PCB this thick, and first they build this PCB and they drill that one, right?
Okay.
And then they build this PCB and they drill that one, right? And then they put them together and they drill the things that have to connect.
Mm-hmm.
So
Mm-hmm.
so it's sequentially laminated two halves of the PCB.
Mm-hmm. Mm-hmm.
Make sense?
Mm-hmm. I understand. Yeah.
I mean, it's kind of a cheap way to do a blind buried via, right?
Mm-hmm.
Just by doing it in the process.
Mm-hmm.
So, but everyone's clear on what back drilling means,
Yeah,
right?
yeah, yeah. So
Okay, because
basically, for example, when we have through hole via, then we can drill out copper until specific depth.
Yes, this big fatter drill bit, believe it or not, goes back up and blows away all the copper. So here we are.
Okay.
And
Okay. Here you have nice
here's
pictures.
a picture. Now this is showing you no, 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 no. Okay. Don't do it like the red X, do it like the green check mark, right? Okay. So I would get designs from people and they were doing their diligence with back drilling, but they forgot one or two, or there was a time when the tools weren't as good and the manufacturing outputs weren't as good,
Mm-hmm.
and you just had to do lots of cross-checking. Okay.
Mm-hmm.
It's a lot more commonplace and a lot more cost effective now than it was, when we started back drilling, maybe around 2010 or so.
So it was not
Um,
perfectly back drilled, for example. Yeah.
yeah, it was new technology, right? You know, I mean, any type of new technology, whether it's equalization or an IBIS model or a back drill or, it we get the bugs out. We're engineers. That's what we do, right?
Yeah.
So here's a picture of a via. I'm really just trying to connect these two traces, right? But I wound up with this stub. Okay, so for very understandable reasons, I get a signal going down here, bouncing off, canceling the signal that's trying to go where it's supposed to go. And so these things can they can completely nullify your signal if they're long enough.
Mm-hmm.
Okay, any stub can do that. So back drilling, like you said, sends that drill up and just gets rid of that extra metal or that stub, right? So this was causing failures at the Gen 3, Gen 4
Mm-hmm.
level, right? And so everyone got really good at back drilling in that stage, all right? Um, but okay, then Gen 5 came along and I I was started to see failures like this, right? Because the trace was over here and it wanted to get to this connector pad, right? So they put the via there. Who wouldn't do that? But that leaves this big stub over here. Okay? So because of the max stub I showed in that other table, well that thing might be 50 mils long. But you can't do that at Gen 5. Now, did it totally stop transmission? No, it didn't. But the bit error rate went way up. Okay, so in product test, people are like, wait, something's going wrong here.
We have generation 5, but works like generation 2.
You said the boards are still being like Gen 2?
Yeah.
Yeah, well, but this is not the board. This is our thinking. This is our layout process, right? Right? So when I choose where to put that via in, when I'm at these higher speeds, I have to go over here.
Mm-hmm.
Now again, don't like you're at Gen 3, don't worry about that,
Mm-hmm.
right? Okay, so again, you have to calibrate to what speed you're at, or you're gonna get more gray hair. You're gonna spend more time worrying about problems that aren't problems. Okay. Like we weren't thinking about that at Gen 3. Nobody thought about that. And sadly, people still aren't thinking about this problem. I mean, look at this thing. These things that might be 60 mils sitting there, right? You got the signal trying to go through here,
So this
right?
is the golden fingers or something.
Yeah, this is the edge fingers,
Mm-hmm. Ah,
right?
yeah, yeah. Okay.
This is the edge fingers right here. Okay, so so that's a stub. That's a stub, right? So please, 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 rest of the world, if we want to keep using edge fingers, we're going to have to mechanically get them more like this, right? Right? We have to get rid of these red areas. Does that make sense? Because
Yeah,
this
yeah.
is showing the signal going off that way. You're going to plug your board in, so the signal's got to go like that. So same idea. You got to get
Mm-hmm.
rid of stubs. So this chart over here, I mean, Eric Bogatin defined this long ago. This is telling you how long a stub you can have at different data rates.
Mm-hmm.
Again, frequency is half the number on the x-axis.
Mm-hmm. And the last one is exactly what I was thinking about, because you have many times you have these PCI Express slots, and I was like, on some of them you still could see the pins coming, through the board out, and I was like, how this is going to work?
Oh, right, right. Well, I mean, I watched the standards above around like 20 gigabits per second. It's all surface mount connectors, you know. Uh, but but the big backplanes used to use the big press fits, right? And so, boy, we spent a lot of time chasing those problems.
Okay, so for
Those,
very high speed SMD, no through holes.
please, yes, right, correct. Very good. I mean, look at this. Look at this. It's like 10, 10 mils has been too long a stub for quite a while here, right? 10 mils, that's like the width of a trace. That's so tiny, right? These things are these are 5 times big more than that, you know? So so yeah, stay safe. Stubs, we might say that's a form of discontinuity that had been causing lots of problems.
Okay, and then next
Was
was
there
crosstalk, if I remember right.
Yes, yes, yes. See, you're right. Okay, right. So here's the issue. Now, it's not that you can't crosstalk in this kind of scenario, right? But that's what everyone worries about, and that's what the design tools handle. Okay? So your layout tool, you probably set some sort of parallelism rule or some sort of gap number, right? They call it different things in different tools. What do you know it as? The gap distance or
Clearance.
what's that?
Clearance.
Clearance.
Yeah.
Yes, yes. So I have to, so this number, uh, people set that to 25 or 30 mils and they just then they don't worry about it, right? And it keeps all your traces so they're not cross-talking sideways. Okay, but here's the gotcha. This is where the problem is. Okay? And tools don't check that. You'll see what I mean in a second. Okay? I mean, the tools may tell you they check, but I'm still I mean I've made the offer. I said here's a board. Find the problem. I'll send the board to whatever tool, layout tool thinks they can find it. But right now they're not finding it. So that's why I say they're not catching it, but humans do.
Yeah.
So artificial intelligence aside, this is something where Robert and Donald can still can still add some value, right?
I
So this
remember I very often, so right now there are some tools which can kind of check the reference planes. So they would highlight places where a reference plane is not located under these signals. But I remember a lot of time I just do it visually. I put them on top of each other and have a look
Yep.
where they are, on top of each other.
Yes. And speaking of, so here's a link failure right here. Okay. Um,
So this is interesting to point out, because this would apply even if people think, oh, I have ground plane directly from both sides of my high-speed signals, but in these places you remove the ground plane and suddenly you see the other signal layers.
isn't that fascinating? Because like you said, we're going to put those are capacitors right there, right? We're going to put we're going to cut out the plane so that I don't have a discontinuity because I
Hmm.
want to match the impedance of my capacitor to my trace, right? So I have to get it a little further from ground. Now, uh, but people hear that and then they kind of overachieve and they might void all the way through their entire board. Okay, so if you're not putting route keep outs in that area, or you're not checking visually like you just said, and like I do, okay, this was a real problem on a PCB, but when I'm doing design reviews of PCBs, I find this all the time because people aren't thinking about it, right? They're not they believe they have a solid plane, but when they, like you said, they cut holes in that plane, now all of a sudden they crosstalk. And think about this, Robert. Like, we're controlling this clearance to 25 mils. Well, if these are layers on either side of a plane layer, these are probably 6 mils apart, right?
Yeah,
They're
because
about
some
six.
of the dielectricum can be very thin.
Yeah, no, I mean, it would be common in the boards I'm working with to have the prepreg or the core, the dielectrics, 3 mils, right?
Yeah,
So you
yeah,
got
exactly. This I wanted.
three
Three
mils,
mils.
then
That's
your plane.
75 micrometers, I think, if I'm right.
Micrometers. This is great. See, we got Europe and US talking right here. So I still think in mils. Yeah. So this chart thinks in mils. So this is really, now this looks extremely technical. Okay, but let me take a chance at explaining it real fast. And that is here. If you have this gap distance of 6 mils,
Hmm.
right? And you have more and more and more coupling from zero. This is not even a quarter of an inch. This is only 200 mils, right? Okay. These are eye heights on this axis. I've completely closed my eye
Hmm.
at 150 mils. I mean, that's tiny, right? That's this, right? Right? This collectively, this adds up to 120 mils, right? So I'm sitting right here on the chart, right? I've collapsed my eye 100 millivolts at this point, right? Now,
This
we
is
already
interesting.
started at the beginning. We said, gee, 10 millivolts matters, right? So these little squares are telling you how many millivolts per mil of coupling. Okay, so it turns out at 6 mils, you're decreasing your eye 1 millivolt per every 1 mil of coupling. 20 mils of coupling, 20 millivolts, smaller eye. Okay, here's a picture of what's happening, right? Basically, you're putting noise in this on the signal, and you're collapsing an eye.
This is important. Yeah, I would never thought the impact is so big on so short distance.
Yes, now we're back here,
Mm.
right? It doesn't take much. This is not to make you afraid, but this is to make you, think that, well, I mean, check stuff like this.
Hmm.
Again, I wish the tools automated this, but that's a very complex problem, right? I mean, someday they will, and maybe some have, and I just haven't met them yet, right? So,
No,
but
I think the biggest problem with simulation would be, mm, I don't know. I'm thinking. Actually, I don't really know how well it simulates the losses. I don't
well,
know.
that's okay. Now, but that is not what I would call simulation. That is a physical. This is just dimensional shapes, types of checking, right?
Hmm.
So I on the last slide I was doing waveforms, but you don't have to do that,
Hmm.
right? You just have to say, you just have to design rule check this, right? Look on one layer, oh, there's a hole. Oh no, I have a signal. I have a signal that's just a few mils away on another layer, right? That's that's just physical checking. Just as this is just physical checking, right? When the tools are checking that clearance. Now this is a lot harder because the tool thinks there's a plane here as well.
Hmm.
So it has, so anyways, this is a nuance. Seems like a small thing, becoming a bigger thing. Like I said, I find the issue a lot uh, when I'm design reviewing, and then I
Hmm.
see the issue uh, when people have a failing link
I
and
would
they
probably
give me a
make this
call.
mistake. No,
No.
maybe, I don't know.
Well,
Because
it's easy to miss.
yeah, exactly. It's very small.
Yeah, yeah. But
And if I would be thinking like it's not big deal, then like, oh, it's only like this. Oh, it's fine.
yeah, so we spent a lot of time talking about that, but you'll do a great job of getting that message out, and the layout companies are going to start calling me. Give me that board, give me that board. It's great. Let's do it.
What do you have on the next slide?
Well,
Oh,
so we can go we can
back to
go
the
back to
yeah,
equalization.
number one.
I don't
So before we talk about equalization, you already mentioned a little bit there is some kind of training process. So how does it work?
oh, well, okay, so that's a great question. It's a very big question because while the electrons are doing the same thing in every type of interface, the training process or the link bring up or the negotiation between a transmitter and receiver, that is unique to each specification.
Mm-hmm.
So when you say how does it work, we can talk about roughly, well, this happens, that happens, but that's the smarts of the specification.
Mm-hmm.
Does that make sense?
Mm-hmm. So like
Um,
PCI Express will have different training specification or description than I don't know Ethernet or
yes.
something. Okay.
You can see all these diagrams and state machines and do this and then do that and then, go here and that didn't work, so try this.
Mm-hmm.
So, but to our point about equalization, um, more and more specifications are trying to auto negotiate the equalization. In other words, that's my first point here. That's the hope that the
Okay.
that the ICs will talk in what's called a back channel. So maybe at Gen 1 data rate, they're testing different equalizations because they don't
Mm-hmm.
they don't know who's on the other end, right?
Mm-hmm.
And they don't know how far away he is. So they're like,
Mm-hmm.
well, I'm going to set myself here and you set yourself there, and then let's see how good the signal is. So they're getting that smart, okay? They're getting that smart to communicate through this back channel means maybe even extra wires. Maybe the spec has some sideband wires that are doing this communication. So there's different ways to work that out. But this is the hope that the ice like I mean, I want to learn this. It's fun to learn this, but maybe I don't have to, right? If the ICs get smart enough. But this is a very technical, detailed problem. Like I work with PhDs trying to algorithmically solve this problem, and it's a very challenging problem. And then you have ICs from different vendors, doing different
That's what
things
I
and
had in
trying.
mind.
you know so I think in the next 10 years, I think it behooves a hardware engineer to, being that this is the secret sauce, this is what makes your serialing work,
Mm-hmm.
okay? So it behooves you to start to learn about this information. So that's why in my book I have a chapter called Equalization Primer. Like, here's the basics, here's what you need to know, okay?
So basically, uh, it means when we switch on our system, there is always some kind of talk between these two chips or between these interfaces, and then they negotiate what kind of speed they are going to use. Or there is this negotiation, then there is the training. Or what's the difference between negotiation and training?
Yeah, there is always some communication that will happen. Okay, I think the big question is, will that communication talk about equalization or not,
Mm-hmm.
right? Because where all this started, the ICs just defaulted. They defaulted. Now, to be fair, most receivers can optimize themselves these days, right? But where all this began, the ICs would go to their defaults. And what was their default? Their default was the worst case, highest loss system, right? Because they always wanted to work. So we had for a dozen years, Robert, we had the majority of systems out there were not optimized because they defaulted to a very high loss
Mm-hmm.
system on a very short connection.
Mm-hmm.
Okay. Because most connections are not these big long things that is the worst case.
And
They're
they
just
could work
simply,
even on much higher speed, but because it was kind of standard, no one really, like USB. I think even the latest USB, they have equalization, no?
oh yeah,
Yeah.
yeah. Yeah, I mean, USB's humble beginnings were so slow they weren't thinking about it, right? It was just supposed to be a little plug and play. Here's how you do your mouse, right? But now everyone wants to connect everything over USB, right? So they have some very high data rates. So they're doing all this stuff
Mm-hmm.
too, but they're doing it industry-wise. They're doing it many years after the problems have already been figured out. Okay, so that's helping. That's helping USB quite a bit. So,
So, okay, so this will happen always when we switch on our system, this
well,
communication.
they'll
No?
talk to each other and they'll figure out if they're working, but they may or may not optimize equalization.
Okay.
And even if they try to optimize equalization, they may just ping pong and in other words, just thrash, we might say, and just not really get optimized. Does that make
So,
sense?
so
Like
how
like
how do we make
not
them
succeed.
yeah,
Ah,
optimal?
you're like, I don't want to live in that world. How do I, how do I, okay. So here's the word, software registers
Okay.
right here. Okay. I generally refer to this as firmware, right? Because, so many times well, sometimes at the standards level, they will tell you where this setting can be set, where this equalization can be set. So transmitters are going to have TX registers, receivers are going to have RX registers, right? That are going to try to set themselves, but you can come in and set them. Okay, you can override them, if you will, right? They're probably going to be most of the time they're going to be unique to your component. So you're going to get a software design kit with your component that it's going to have registers that seem way more important. And then it's going to have some equalization registers in there, right? And so if your equalization is not working, now this is a gross oversimplification, but step one, go figure out how to access your TX equalization register, right? And like, well, that's easy. Okay. Well, in a big company, it's not because the software is controlled by someone on the other side of the planet. Okay. In a small company, you probably, yeah, if you're a hobbyist or whatever, you've got the whole thing. So you can find that register and you can program that register, right? Okay. So oddly enough, because receivers are so talented and such good technology, if you can get to that TX register and shut that off so that he's just sending a signal. He's just sending the best amplitude signal into the system that he can do. Okay. And he's not, equalization hurts his amplitude, to put it simply, right? So if you can just let him broadcast a signal and let the receiver handle it, that I've fixed lots of problems that way. I fixed that crosstalk problem I showed you.
Mm-hmm.
Okay, because what I didn't show you is that the red signal. Well, I'm going to show you right now.
So why they don't design this the best way when they set up the chip or something? Why the
Ah,
register default is not the best one?
well, okay. Think about it though. Like,
Power consumption, or I don't know.
no, no, I don't. I'm just a chip. I don't know what system I'm going to be in. I might be trying to equalize 2 dB, I might be trying to equalize 20 dB. It might be 35 dB. So how do I pick the right default? How do I
Mm-hmm.
pick the right number? And that's why I say they just chose the 35 dB number.
Mm-hmm.
Boom. And everything's over equalized because most systems are, maybe 6 dB,
Mm-hmm.
right?
So we are
Okay.
talking, for example, about distance between the chips. Yeah. So default, they maybe preset to the maximum distance, or I don't know, but
Yeah,
our chips.
distance. Yeah, distance is the simplest way to think about it, but there's a lot of factors in there. I mean, that would be another great whole topic for you and I to go into, right? Like where, oh my goodness, where does this loss come from? I mean, I had one chart. Now we're bouncing around, Robert. This is getting fun. I had one chart. There it is. Right? Now this is Gen 3. No, sorry, Gen 4, right? So these are the kinds of numbers. These are all assembling and adding up to about a 20 dB
Mm-hmm.
system. So this is kind of showing you, oh, I have different kinds of traces.
Mm-hmm.
Wait, I got 7 inches with 4 dB here. Here I only got, 4 inches. Okay, so depending on your dielectric, you may get that's what it says right here. The loss tangent right there, it's changed 10x in a short amount of time. Okay, so that's why I say the answer is yes, length is involved, but I can have. I mean the cables have 10x less loss. I could get 20 inches on a cable that has the same loss of 2 inches on a PCB. Like think about that for a
Wow.
second. A 1 meter cable is like a 4 inch route, like a good 4 inch route. That okay? So yes, length, but
I
you know,
understand. I understand now.
okay, all right.
Okay.
So
So it's not
so
only
let me
length.
let me finish the
Length is not the
thought.
best example. Okay.
Let me finish the thought here. This red signal, this is a TX right here,
Mm-hmm.
and he's really close to his VGA. So this is like loss hasn't impacted this. This
Mm-hmm.
is like a fast edge. This is lots of energy, right?
Mm-hmm.
And here, this blue thing, this is the RX
Mm-hmm.
coming from the other side, going into the chip.
I see
So
the
we have
problem.
this, yeah, bad feedback. We got a very powerful TX hitting an RX that is just about to get received,
Mm-hmm.
and so that's a lot of coupling,
Mm-hmm.
right?
So even the direction is important and location where we are looking at.
Yeah, yeah. And so for many years we've put TXs and RXs on different layers for
Mm-hmm.
that reason. So they don't so they don't crosstalk on each other, but
I've
here
done
it is.
this.
They're on different
Yeah,
layers, but
I've done
they're
this. But
all
even here
right.
they are on different layers. But you see there are the
Yeah,
openings.
yeah, exactly. Exactly. So now this wasn't the final fix, but I said, okay, just try shutting off that transmitter's equalization.
Mm-hmm.
Okay. And sure enough, that was enough to solve even that
Mm-hmm.
problem. Okay.
So this is interesting. So maybe when something is not, some hardware is not really working as you would expect, there's still maybe chance to do some software changes and make it work.
Yeah, I think that's perhaps my funniest article at Signal Integrity Journal. It says fix signal integrity problems in software. Right? Like,
So
wait, that's impossible. That's impossible. Okay, but
before we okay
that's that one.
I see. Uh, so how do you change it? Like there are some utilities, or how do you access these registers?
Yeah, that's well, in the data sheet for the component, it's going, or the programmer's guide, it's going to show you these registers, right?
Mm-hmm.
So how you get to those registers and how you get to that part, that's going to vary system by system.
Mm-hmm. Mm-hmm.
Okay. So there isn't a nice simple answer there, and this is why it's seldom done. Okay, but if the system's not working, people find a way, right?
Hmm. And in like standard boards, like I don't know, PC board or something, all this is done in BIOS or how it is done?
Oh, well, okay. So an FPGA, for example, is gonna power up and go grab its flash.
Yeah,
You
yeah, yeah.
know, there's going to be some persistent whatever that's going to program and configure that FPGA,
So you change it
right?
directly in firmware of the FPGA.
Yeah, 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 yeah. So I would say most of the time it's firmware, but now I'm getting out of my lane a little bit.
Okay, okay.
Okay. I'm here to tell you it's somewhere. Okay?
It's very good tip actually. I wouldn't think about this. So
Right.
this can also help with even like PCI Express.
Absolutely.
Okay.
Well, sometimes sometimes the specification dominates and doesn't, or the component, when you say, okay, you're going to work in PCI Express, then it dominates and it doesn't, it thinks it is the only, it thinks it's the king, the only one who gets to touch those registers, and it might lock you out.
Yeah, yeah.
Okay. So I think a clever person can still find their way.
But okay, I have a different question. How do you know this interface is working at the highest speed?
Oh, it'll tell you that. And there's, uh, well, again, registers, right?
Mm-hmm.
But it will tell you that, and certainly a what's called a protocol analyzer, who's, you know, a lot of times in the lab bringing up these things, you'll hook up a protocol analyzer that's watching all the traffic, and that will tell you,
Mm-hmm.
oh,
Mm-hmm.
we made it to Gen 4, we made it to Gen 5.
Mm-hmm.
Make sense?
Mm-hmm. I thought there is some kind of test software or something, but yeah, probably once it is set up and working properly, you can read somewhere from a register what kind of speed or generation it
Right,
is running on.
right,
Okay.
right. So isn't that funny though? I mean, signal integrity used to just be traces on a PCB, right? So so that's what I mean, if people walk away with anything, I hope it's become clear that a lot of signal integrity now is inside the chip, right? It's inside the chip, which by definition sort of means registers and software. Okay.
That's interesting.
Yeah, it's
And you
a,
put this on
yeah,
first on the top of your list, so I guess it
absolutely.
really helps.
Absolutely. Even though we don't want to do this and it's a pain to try, I mean, like I said, this is the dominant failure mode and the dominant way that I have fixed and improved links. I mean, gosh, it was 2014, 16. Like we showed papers, we were improving performance 200% simply by manipulating the equalization.
Mm-hmm.
There's just lots of margin available out there when this is done right.
Mm-hmm.
Okay. And so margin becomes also correction or fixing failures, right? I can have margin that helps me across manufacturing variables, or I can simply increase my margin and make the link work again, right?
Mm-hmm. Mm-hmm. Okay, so what do you do actually? What's your job? I'm curious.
What do I do?
Yeah, yeah, yeah.
Oh, me personally.
Yeah. I think you have first slide. I think I've seen something on first slide. No, do you have something or second slide?
Well, uh,
Oh yeah, I've
well,
seen
this
something
this
here.
gives this one says a little bit of my background, but I've been in signal integrity for 40 years. And you know what? I was thinking about this last night. What I really do, ever since, so in 1991, I get the call. I'm working at Intel, and they're like, "Hey, we got to make the PC go from 8 megahertz to 33 megahertz, right?" And like, that's what I do. I have doubled data rate more than a dozen times. So I'm not maybe out there, figuring out how to do 500 gigabits per second, but when it comes time to actually productize and manufacture and get this thing into volume, I've been there at every data rate jump, every iteration to try to make it figure itself out. Like, not the gee whiz, oh wow, we got these things to talk. No, how do we get them into production? How do we ship product with these things? That that's what I've done for decades. Does that answer the question? That's
Yeah, yeah, yeah. But you now you do consulting, so you don't work in Intel anymore.
No, no, I've been consulting for 20 years. So I was at HP and Intel and Cadence for my first 20 years, which taught me the whole industry from every side. Think about it: systems, ICs, and EDA. These are the three. These are the three, you know, parts of the triangle that make electronics work. So I got to work in all those domains, right? And so then I started consulting. So for the last 20 years, I've been consulting. And I think the interesting news is that, boom, I'm stepping out of my design cave, and I'm gonna start teaching these things around the world.
Cool.
First in first in the U.S. In the fall, we're gonna go to Europe. Hopefully next spring over to Asia, right? So there was a world, Robert, when engineers used to talk to engineers and get in the same room and like we're doing here, we're succeeding at communicating. But no, I mean I worked at Hewlett Packard when Bill and Dave were walking around the aisles, talking to us. This was the beginning of technology and engineering. So we're bringing some of that back into the modern world. And yeah, I'm gonna step out and some of the things we talk about today, but of course a lot more, and of course the content and topics in my book, which are much more practical than theoretical. Like here's what yeah, you have to understand XYZ. You have to understand there's equalization registers, right? But once you find them, what on earth are you going to do? Okay, so these are the topics of the class.
Mm-hmm. So what else you have in the slides? Did we miss something? Or
Well, we didn't do the deepest dive in equalization.
okay, okay, let's have a look.
Uh, all right. So this is saying, go start to, you may not feel very PCB-ish, you may not feel very signal integrity-ish, but go start to learn what these terminologies are. This is just as important as stack ups and return currents and the stuff that we've traditionally, in what I'm kind of starting to call old school SI, these are mostly givens now. People use solid planes. We have return planes. We have, you know what I mean? Stack ups. Yeah, stack ups. There's some stuff to think about. And yeah, that's kind of where impedance comes from. But still, that's not what's making your system work. The things making your system work are up on this line. So hopefully that's become clear. So that's an encouragement to, like I said, there's a chapter in my book, but these things you can learn anywhere, right?
I will need to
Um,
search on internet. I
yeah, it's
only know
really
VGA, but I guess that's not the VGA what I know.
variable gain amplifier, right? That's not the VGA, you know. Um, so the other thing to think about, and I've said this multiple times already, even if the transmitter and receiver can't talk to each other, receivers are getting really good at self-optimizing just in their own space, right? But if the transmitter's not doing some basic things, such as precursor, okay? Now this means it's equalizing something that happens before the bit even came out, right? So the RX isn't smart enough to know what data it's about to receive, so it doesn't know how to equalize that. But the transmitter, you know, Well, of course, it knows the data, right? So it can do things before the bit even happens. Why is that? Okay. Now this looks incredibly complex. So let me try to take it apart, right? So so this x-axis is in time, but it's in unit intervals, or we might say bits. So every tick mark here is the next bit of
Mm-hmm.
information. And so this is a pulse response. So all we've done here, we just had the interface sitting at 0, and we sent a single 1. Boom, right? Wow, there it is. But look at this. Look at this. There is, because of pulse spreading and because of the losses and the noises in the system, a lot of that energy that we wanted right here at time 0, which is the bit we care about. Oh my goodness, some of it spread before the information even was there. Wow. Now, a lot of it spreads like, look at this. 60 bit times later, Robert, I still have so many millivolts, right? So every millivolt at every bit here if you think about it over time, they are all in the right sequence of bits, they're all shrinking my eye by that amount.
I understand now. I understand this graph. So
Ah,
basically, this is only some kind of one bit, and we can see the influence on many other bits around.
right. And that's what we call intersymbol interference. That's what we call the bits colliding with each other, and
Mm-hmm.
that's what shrinks the eye. Now, loss and discontinuities shrink the eye in different ways, and they cause very different pulse responses, and that's what red and blue are showing you, right? So if I just have a lot of attenuation, I wind up with this very long tail, but it's kind of linear. It's sort of understandable, right? It goes for a long time, but that's what loss does, and it shrinks your eye into something you just can't find, right? Now, when there's lots of reflections and lots of discontinuities, I mean, look at that chart. It's sometimes it's adding to your eye, sometimes it's subtracting. It's just like it's waves bouncing all over the place, right? So look at how that closes your eye.
Mm-hmm.
Ah, right? It's not this attenuated shrinking thing. It's just this jittery, I don't know where the opening is. I don't know where the signal is because there's so much reflection. There's so many discontinuities in the system. You see the difference between those? You see the red and the blue?
So
Is that
basically, the
making
red
sense?
is still the influence of the one bit, but as it travels through the channel, there are different influences from the vias and all the other
Oh,
things. So
yes.
it's not like linear, but it's going to be. Mhm.
Right, right. Now,
Okay.
what I should have said at the beginning, Robert, is red and blue are two different types of channels. They're two different channels. They're two
Okay.
different connections. Okay. One just maybe is really long with a lot of loss, right? The other might be short with a whole bunch of,
Okay. Okay. I understand.
discontinuities.
Okay.
Okay, so these are there's the blue system and the red system,
Okay.
right? And so that's why this is making the point of, if you want to understand your system, then look at its fingerprint. That'll tell you what it is. The fingerprint is the pulse response, right?
Mm-hmm.
If it looks like blue, oh no, I have a lot of loss. If it looks like red, well, I've got a discontinuity problem. I got a bunch of noise. Now, um, probably when you look at your system, you're going to see something that's a blend of these two things, right? You're going to see some loss, but you're also going to see a little bit of ringing or noise due to discontinuity. Make sense? But it turns out that, you know, when I understand this fingerprint and I understand equalization, well, I know exactly how to set my equalizers. I know in bit 5, in both of these, in bit 5, okay? You see bit 5 right there?
Mm-hmm.
I got 40 millivolts too much
Mm-hmm.
positive noise. Okay? So if I have an equalizer available to me at bit 5, I gotta knock that down 40 millivolts. And so basically equalization, I didn't show an equalized pulse response here, but basically the equalized pulse response just pulls all this stuff back down to the line.
Subtract all these errors and
Yeah,
okay.
right. Noise. Yeah, it's intersymbol interference. So the equalizers simply bring this all so that all the energy, all the voltage is all in the bit I care about. But you think about, so this also tells you why equalizers do a much better job at loss than discontinuities, because wait, this is a serious problem. First it's low, then it's high, then it's low, then it's high. So I have to kick this thing depending on how many bits out. I have to kick this thing in different directions, right? And oh no, it's way out here. I got like 10 millivolts over here, way at 50 bits down the road. That's crazy, right? So they have these things, they're starting to put these things called floating taps that go hunt for the noise. They float, they go down, they look down the pulse response, if you will, and they go, boom, there it is, bit 50. I'm going to get rid of that noise. I mean, this is, in some ways, this is just basic signal processing, but again, this is a YouTube about signal integrity, right? But this is what makes things work and not work.
You know what I'm thinking about is you have to do this calculation or adjustment for every single bit until the bit 50. So it must be quite.
Okay.
I don't know.
No, it's not that bad. Let me tell you why. Because when you fix the first one, when you fix the first bit, that impacts how bad the second, third, fourth, fifth, that affects how bad the other bits are, depending on the type of equalization you're using. A continuous time linear equalizer, boom, that's going to affect the entire thing, right? And so different types of equalizers do different things, some only at the bit level, some at the multiple bit level. So we've written papers about that and how to interplay those and how to be smart about all that. But this is the mechanics, and it's not impossible. If we didn't have millions of extra gates laying around our silicon, it might be impossible. But basically, that's how it's being solved today.
And can the firmware or the training or I don't know what do this fingerprint and set up the equalization by itself, or you have to do it somehow?
Well, like I said, that's the hope.
Okay.
Okay, but in the hands-on labs in my class, Robert, this is what we're going to do. I'm going to give you different channels, and we're going to go equalize those things, because this is the new signal integrity. This is what I have to learn about, right?
Interesting.
So let's say the ICs don't do it, okay? As I've many times had to do it by myself. Well, hardware engineers obviously need to do that too, right? So this is why we're gonna, oh my goodness, we're gonna try to do this. We're gonna bring up those tools.
That's interesting. It may be interesting to know how do you come up with the numbers which you need to then use in the equalization to set it up correctly.
Yes.
I guess that's your training about.
Well, yeah, but I mean, in some ways, I also told you, I can off this chart, I can read the level of the problem, and that translates into a register setting.
Okay, are there some other slides what we missed?
Well, let me
Maybe
look
we went
around.
through everything.
We've been on a wild ride, Robert. Oh, can I say, okay, so for the engineer who's like, wow, that whole equalization thing, oh my goodness, you know, uh, believe it or not, I've turned the process into 7 steps. Okay. Um, and so I tell the story in the book about where those came from. But basically, all these things just help you manage loss and discontinuities at different points in your design cycle.
Hmm.
Okay. Like where do these things come into play when I go build it? Right? Step 6, fabrication problems. There's
Hmm.
things to think about there, right? The whole the whole equalization thing. I mean, I called it engage your firmware team. You may be your firmware team, right? But, but recognize there's this whole software side, right?
I didn't know before we had this call. I would probably never think too much about how important it is to actually have a look inside of the firmware and registers.
I mean, this is that's what this picture is showing and the importance the importance is only increasing with data rate too, right? Right? It's not becoming less important. It's becoming more important. Like I said, now, the Gen 6 is going to be it's like 5 times more equalization than Gen 5. Crazy, right? Whereas the PCB is almost doing the exact same thing because the fundamental frequency is going to be the same, right? But now it's going PAM4, so the equalization is now like 5 times more powerful.
I was exactly thinking about this because, uh, again, we may need to explain. PAM4, it means there are 4 different levels, correct?
Yes, encoded, but yeah, I don't have a slide on that right here, but Google PAM4.
Yeah, so it means it's not going to be only like 0 and 1, but there are 4 different levels, and there will be really signals with 4 different levels, and this equalization, it has to recognize which one it is.
Right, but I mean that in itself tells you like the PCB process is rather resistant to change, right? It's not like stepping an IC. It's not like going to the next node of nanometers where I have all kinds of new capabilities. Like these are drills. These are drills and glue, right? Then
Yeah,
you
you
just
are
go to
right.
a PCB factory, right? It's plating. It's like it's not nanometer
Yeah, and
silicon
it's not
gelder.
going to be. I don't think PCB is going to be much smaller because there are some limitations. So
Yes,
it has to be
yes.
done differently. So in
It's
software,
my
for
world.
example.
It's my world, and I love it. But at the same time, it is very resistant to change. The PCB process is very resistant to change. Like I'm starting doing this in the mid 1980s, and we're hand taping traces, but they're 12 mils wide. You know, I mean, now I'm working with 5 mils. That's not a big change, right? It's more automated, but it's not that's not a billion times more transistors, right?
Yeah, I think there are some reasons why it's not like, for example, I don't know, you just bend the PCB and suddenly everything will break if it's like too tiny, or it just, maybe,
Right.
I don't know.
Yeah.
Hmm.
Yeah. It's
Okay,
it's it's stuff
so
you touch.
we went through everything, correct? It was the last slide.
Well, and I hadn't showed my book yet, or maybe, yeah, I guess I did. I mean, this is just me, where to find me, you
So
know.
if someone would like to learn more, or maybe go to your training, or maybe have some problems and they would like you to help them to solve these problems, this is where they contact
Yeah.
you, correct?
Well, the answer is if you want to talk to me, then you can come here.
That's your website. Yeah, I
If
think.
yeah, and if you don't want to talk to me, you can just keep the book. But like I said, we used to talk with Bill and Dave, Hewlett and Packard, like so. Talk to me, like it's I think I've proved I'm really here.
Yeah. So definitely, if someone is working with all this super high speed, or they have problems even with PCI Express, maybe you can help them. Okay, so thank you so much, Donald, for this
Oh,
information. I learned a lot. I had no idea, for example, how equalization works and how important these firmware settings are. So thank you very much for this.
very good. Yeah, it's an honor. I appreciate the chance to talk with you, Robert. Love what you're doing, and yeah, I mean, at the end of the day, I hope and trust that we've helped your viewers.
Okay, thank you.
Yep, thank you.
And that's everything. Thank you very much for watching this video. By the way, we are preparing some very interesting tutorials, so if you don't want to miss them, hit the subscribe button. If you want, you can also check out our FedEvel online courses, where you will find everything important from basic board design up to advanced hardware design and PCB layout. The link is in the description. That's all for this video. Thank you again. Don't forget to leave your comments and see you next time. Bye.